We're Group 8, and this is our ECE 4534 Embedded Systems project, World's Coolest Cube. I'm Ryan Marlow.
I'm Scott Luxenburg.
I'm Ben Hummel.
And Kenan Pulak.
This is our cube that has sensors that detect motion, LEDs, and the capability to play audio-sound files. It is also equipped with a wireless transmitter, which it communicates with our stationary microprocessor, which then relays to the arm. And so we can send data from our gestures to the arm, and it'll relay back messages of responses based on those gestures. And those responses will be shown by the LEDs and the sound file that's played.
So for our project, I designed the PCB board, which is the hardware of the project. Here is the board itself. On the board is the PIC 18F45J10 microprocessor. The microprocessor communicates over a number of different communication protocols to our sensors and our outputs. The sensor that we have here is the IMU. That's an accelerometer and gyroscope. It detects motions of the cube. As far as outputs go, we have the blink M's, which also communicate over I2C. They're LEDs that you can send them pre-constructed scripts, and they do a variety of different things. Right here, they're in their default script of going through white, red, green, blue. And then finally, our other output is our other output module is the audio sound module right there, which has a micro SD card. It reads music files from a micro SD card and plays them on our speaker, which is embedded in the cube right now. So to send sensor data and receive output scripts and music files, the cube transmits wirelessly over this XB module right here, which communicates with the microprocessor over the UART communication. So I'll just put the cube together really quickly. Just show you that. So here's the cube, fully constructed, put together. As you can see, I made some. I attached each of the LEDs to all the faces, and then the speaker, the output speaker. I drilled some holes so you could hear music stuff. What's really cool about the cube, I think, worked out really well, is I bought this thing called a power mat, which the whole point of the power mat is just sort of supposed to put a device on the mat and then it starts charging. So I have this little adapter for the power mat. Just set the cube on it, and then the battery is charging right now. So that's pretty cool.
Okay, my contribution was XB, EasyVR, and software UART. XB uses UART protocol to send messages wirelessly from the stationary PIC to the cube PIC using IEEE 802.15.4 communication. And since it uses the hardware UART port on the PICs, and the PIC 18F45J10 only has one hardware UART port, a simulated software version of UART needed to be configured using general purpose I/O pins for the EasyVR speech recognition module to work into the project. And the EasyVR has a specific setup and wake-up procedure that needs to be initialized prior to reading in a voice command, and you need to specify in the wake-up procedure the language and the word sets that will be accepted by the EasyVR module, which will then send the message to the software UART on the PIC.
My responsibility was programming the cube PIC and the stationary PIC. Some of the devices I programmed with was the IMU, which contained the gyroscope and the accelerometer, and also with the op amp and the blink amps and the audio sound module. Also, I programmed some of the UART communication with the XB on the stationary pick. I used a timer to pull the IMU data off, and also used a timer via I2C, and also used a timer to pull the op amp. All that data was formatted and sent and relayed through the stationary pick to the ARM. Commands were relayed back through the stationary pick to the Q pick. Blink-M commands were via I2C, and the Blink-Ms had several different light scripts. And then using a serial communication that I created myself, music scripts were sent. Music files were selected on the micro SD card on the audio sound module.
Okay, my primary responsibility was to deal with coding all the code on the Kyle board, as well as any related stationary pick code to I2C transmission. The way all my stuff works is when the cube sends out any signal from any of the three devices, the two IMU devices or the op amp, what it does is sends it wirelessly to the stationary pick. And there, the stationary pick code I wrote takes that UART message, passes it directly to I2C, and from there it goes all the way to the Kyle board. At that point, the Kyle board will read it, determine if an action needs to be taken by first identifying the device that comes in, then from there using a set list of thresholds to determine what action has specifically been taken. And then at that point, it's also going to print out the specific action on the LCD screen. So print out right, left, up, right, left, next, previous, and random, and it'll show the value that triggered it. At that point, the ARM will determine what action is going to be coming back, either a Blink-M or ASM action, or possibly both. And we'll send it back through I2C to the stationary pick. Then the second bit of pick code I wrote for the stationary pick will take that I2C message and pass it directly to UART, which will send it out to the cube, and then the cube will either perform a Blink-M action, play a different song, or perform both actions.
So this is the world's coolest cube, our project. I'm going to do a quick little demo of its capabilities. So I just turned it on. So when I just turn it on, the Blink-Ms play their default light script, which is white. It iterates through white, red, green, and blue. It's not actually receiving any messages. It's just when the Blink-Ms start up, they start up this light script. And so the IMU, like I said earlier, it detects motion gestures of the cube. And right now I'll just shake it up and down. When I shake it up and down, it's going to play a random light script and a random song from our song list. So let's go ahead and do that. So right now it's playing a song, it's playing a little light script. I think this is shades of blue. So you can see the LEDs are kind of changing colors a little bit. It's pretty cool. Next I'll show when I rotate the cube clockwise or counterclockwise about the Z-axis, so up and down, the light scripts are going to change to single color flashing. And then there's a number of those that I'll iterate through to show you that capability. There we go. Okay, so right now it's red, green, blue, and then when I go back the other way, it should play those it should show those same light scripts I just iterated through. So there's green again. Yeah, so there you go. And then when I move the cube left or right, it'll play a different song. This can also be done by just sort of rotating the cube so that it's, I guess, so that the IMU receives G-forces from the X or Y axis instead of the Z axis, which is what it's doing which is what it's receiving right now. So I'll just do that. So right now it's playing a song, and then go to the next one. This is the next one. It's a pretty quiet song to start out with, but I'll just show you. This is so previous and then previous. So there you go. That's pretty much the capabilities of the cube. I'll just end off with another random.
I'm going to talk real quick about the capabilities and the limitations of our project. As far as robustness and component failure, sometimes the stationary pick would get off a little bit, but the cube pick and all the functions of the cube would continue working. And then with reliability and operating in different environments, the cube would work in other rooms and a good distance away from the base. Also with reliability, the cube would continue to work even when the stationary pick or the arm failed. At times those would fail though and get off a little bit, and the stationary pick had to be reset.
What we can improve is by making a better handler system on the stationary pick, so that the stationary pick would be detecting that this is not the case, and when this is actually occurring, it would actually stop all communication, allow a cube message to come through, so therefore the device ID would be reset back to the first position, and when that reset occurs, then it would automatically resume transmission, so we would not need to manually reset, and downtime periods would be a lot less. One feature we had planned to implement but was not able to implement due to difficulties was a MATLAB data recall feature, in which the cube data which is displayed across the LCD would actually be transmitted to MATLAB upon request. We tried it through two ways, through USB communication and then through TCP connection using the built-in web server. The USB connection failed because when we tried opening up through serial port communication, the computers were not actually able to make a direct connection with the arms. We had to abandon that idea. The web server was the closest idea because we actually got a web server up running and was able to display different sources of data. What happened is MATLAB was not able to make a direct TCP connection to that web server, and since we could not make a connection, it couldn't open up and actually store the data. So therefore and not to mention, that was only one way, that would only be opening the data. We were also supposed to have the functionality to send data back to be repeated, and that when that data was sent back, it would cause the cube to play back that entire segment that was inputted. But since there was no way to actually feasibly do the input, and since the TCP was blocking and not allowing a full connection on the sending, we just abandoned the MATLAB idea. So if we had time for more improvements, we probably would spend more time actually working on the web server to find a way to open the TCP connection so that MATLAB could directly connect.
So one other thing that we couldn't get into our project was the EasyVR, and that was because our PIC only has one hardware UART communication module, and EasyVR also uses UART, but that hardware module was being used by our XB communication. So in order to use the EasyVR, we had to set up a software UART which would use the two general purpose I/O pins as RX and TX receive and transmit pins like UART has, and we would have to do that programmatically and kind of make those pins act as a UART communication protocol. And so that was the reason that we couldn't implement the EasyVR into our final design, was because of that software UART not being able to function correctly. And another issue with that, with the EasyVR, was during the setup and wake up procedure, it would block the other communications that were going on in the cube. So in order to do that, in order to implement the EasyVR, we would have to have some way to wake it up and do the setup procedure and the wake up procedure, which is a very specific thing for the EasyVR to be able to read in a voice command, and we couldn't get that part to function in our complete design. And something that we could improve upon would be to have either another extra hardware UART, or another thing would have been to get a different type of voice recognition module that didn't use UART and use some other type of communication protocol on the PIC.
And that's our project!
Done.
Alright.